Am I audible to all of you guys? Okay, cool. So let me share my screen. Uh, is it visible to you guys? Okay, great. So let's begin with the session, guys. Yesterday we saw the internal architecture of RNN, and then we saw what is the internal architecture of LSTM and how it is different from RNN. So we saw there are couple of changes in this LSTM architecture with respect to RNN. So we have something called as a memory cell whose output is a cell state. And then we saw there are three gates: forget gate, input gate, and output gate. So in that way, we have this kind of a internal architecture of LSTM model. And then we also saw one of the practical hands-on over LSTM model, how you can do the forecasting, right? So up to that point, guys, till last session, any doubt or any questions, any queries, anyone, or we are good to go? Okay, so no questions, I guess. Great. So let's begin with today's session, guys. So today, there are two objectives. So first of all, we will see how you can utilize this LSTM model over the text data. So if you want to, process the text data, which is the sequence, which is it's a sequential data. So if you want to do, certain kind of analysis using deep learning technique over the text data, how you can do that. Okay, this is first thing. And then we will see, a couple of advanced version of this LSTM, not advanced version. So it's a like where this LSTM architecture is utilized with respect to the generative AI. So I'm talking about sequence to sequence model. And then we will try to understand what are the advanced form or modification has been done over the sequence to sequence model so that we have some other architectures. So this is the agenda. So let's start, guys. So first of all, we are going to see how you can use this LSTM architecture for text data analysis. So let me reshare my screen. Okay, cool. Uh, is this Python notebook is visible, guys? This Jupyter notebook? Great. I'm sure the like the size of this notebook is now it is very much clear to you guys, right? What is written, all of these codes and all. Okay, great. So guys, what we are going to do, so this is another case study. So we have a text data, which is it's a sequential text data. Uh, so we need to analyze this text data in terms of the text classification. And we are using the deep learning technique to classify our text data using LSTM model, right? So if I just quickly show you our input data, so we have a data set like this. So just ignore this ID, keyword, and location variables. Just ignore this one. These are not are of no use. So just focus over these two features, guys, text and target. So this text is nothing but whatever input text data we are getting, right? And we need to classify all of this text information either 0 or 1. So here, guys, 1 indicates, so if you're classifying particular document or text data as a 1, that means there is some disaster information is available. So you can see the first information or first document. So there is a things related to the earthquake, right? If you see second document, here we have something called forest fire, right? So likewise, we have a things related to the disaster. So if that kind of a context is present in this input text data, so that is something we are classifying that as a 1. Otherwise, we are classifying as a 0. So 1 indicates that there is a disaster information is present. That means there is something with respect to the disaster, and 0 is nothing but not a disaster, right? In that way, we have a target variable either 0 or 1. In this case, what you are seeing, it is just a head of this data set. So like first couple of records are categorized as target 1 only. But yeah, we have a couple of like documents which classified as a 0 only. That is not for disaster. So in that way, we have this data, and we need to build a model which will classify each and every document whether this document belongs to the disaster one or not a disaster. So that's why we are calling this one as a text classification model. And we are not going to use machine learning technique. We are going to use the deep learning technique, right? And one important thing to note here, guys, in this like exercise, I'm not going to perform text data pre-processing part. I'm repeating it again. I'm not going to perform the text data pre-processing part. That is something you can do at your end. So it's not like there is no text data pre-processing is applicable here. That part is there. You need to apply the text data pre-processing part before applying any kind of a model, right? So since I have already covered that part, so just to save the time, I'm not going to apply the text data pre-processing part. Now, can you guys tell me what are the different things are there in the text data pre-processing? Do you guys recall? Anyone? Yes. So lemmatization or stop word removal, punctuations removal. So those kind of things are there. Okay. Yes, you are correct. So tokenization and all. So I'm not going to perform, guys, that kind of a part. So you can do at your end, right? So I'm just jumping to the next step. Okay, so let's proceed. You can also check, guys, like how many documents belongs to class 0 and how many documents belongs to class 1. So with the help of the value underscore counts method, you can check for a target variable, that is this one. How many documents or text information belongs to class 0, that means not a disaster. So there are 4,000 plus documents which are classified as not a disaster. And there are around 3,000 plus documents or the text, input data, which is categorized as a disastrous document. That means the document which contains the information related to any kind of a disaster. Yes, guys. Vectorization is not a part of text data pre-processing. So when we talk about the text data pre-processing, that means how we clean the data. So once we clean the data, then the next step is a vectorization, right? So vectorization part is there. Okay. And then if you want to shuffle the records, guys, although there is no requirement to shuffle these records, but yeah, if there is a requirement, you can shuffle them. Not any harm, right? Since we are not taking any time instance in this case. Okay, so you can skip this part or you can go with that. Both things are correct, right? Okay, anyways. So let's see what next we are doing. So in this case, in this particular part, we are just, visualizing any random 5 documents. And how we are visualizing? So what it will do, it will randomly select 5 documents out of, total number of documents, and it will show what is the text messages there. That means what is the sentence present. And then it will also show me what is the target value. And here I am just modifying this target value as if the target value is greater than 0. So there are 2 values in the target variable, either 0 or 1. So if the value is greater than 0, that means if the target value is 1, so just show me it is a real disaster, right? This is a encoding of 1, right? So 1 stands for it is a disaster. And if the target is 0, it will be not a real disaster. So I'm just printing this kind of information also with my text data. So if you see the output, guys, here, so it will randomly pick 5 text documents. So one of the document is picked as this one, and it is a random, guys, right? So the number of times you run this particular line of codes, you will get different outcome because it's a random selection. So here you can see, guys, this is one of the document, it is selected. This is another document selected. This one is another document, and we have 2 more documents, right? And for each and every this text data, we have the target variable either 0 or 1. And this is something we are getting because of our code. So we have just modified, if the target value is 0, just print not a real disaster. If the target value is 1, just print it is a real disaster, right? So this part we are getting because of the code. This part, this information, right? Guys, is my voice is clear? Just a minute, guys. Okay. Yeah, I guess my voice is clear, right? So Sumana, if you're facing an issue with voice breaking, please check your internet connection. There is one question from Himanshu. What is the benefit of shuffling the records? So guys, why we are shuffling the records? Because, so I mean, it is not beneficial in this particular case. But sometimes what happen, if you have a let's say for example, let's suppose you have a data set where let's say you have a 100 records, right? Let's say you have a 100 records. Let's say the same example, you have a text data, and each data is classified either as 1 or 0. And let's say you have in that, like we have 100 records. And let's suppose whatever data you are getting in that 100 records, first 80 records, that means first 80 sentences are classified as 1. There are no zeros present. And the rest 20 sentences are classified as 0. So now how we build the model? We divide our data into train and test part, right? And guys, one important thing is there in case of a sequential data handling. So when you are handling the sequential data, we never divide the data set into train and test part randomly. Randomly means like we divide the data set into train and test, but not in a random manner, but in a sequential manner. Sequential manner means we take the first couple of records as the training data set and the rest of the records as a test data set, right? While in case of a cross-sectional data, so if you recall the ANN example, in case of a cross-sectional data, guys, we also have a train and test data set, but in that case, the splitting is random. That was not a sequential splitting, it was a random. So it will randomly pick 80% of data in the train part and the rest 20% data in the text part. That is with the cross-sectional data, because there the order is not important, right? So if you're not shuffling the record, and let's say you are getting this kind of a data set, So probably what happened, uh, in your training data set, you have all the data which is having the only one category, which is one. So your model is not able to understand what is the zero, which is very rare condition, right? In practical cases, we will never get this kind of a situation. It's very, very rare condition. But yeah, just to avoid this possibility, we are shuffling the records. But in this case, as I told you, in this case, no need to shuffle the records. You can skip this part. Okay, so this is an optional step. Lokesh, I have no idea when the surprise test will be, it is being conducted. So it is being decided by the operations team. Okay, cool, guys. So let me just increase the font size. Okay, cool. So this is how we are, visualizing this text data. Okay, this is just a simple visualization kind of thing. Okay, so here we are just splitting our trained data set into two parts: training sequence and validation sequence, or let's say train sentence and validation sentence. So what we'll do, we will build our model over training sequence, and we will validate this model over this validation sentences. This is what we are going to do. And apart from that, guys, I have another data set, which is the text data set. So you can also validate your model over this text data set, right? So what you can do, you can build your model over this complete trained data set and validate your model over this test data set. Or the second approach, what I'm going to follow here, I have taken this trained data set and I've splitted this data set only into two parts. Again, train sentence and validation sentence. So I will build my model over this train sentence. I will validate my model over this validation sentence. If my model is performing good, then I will apply my model to test sentence. So that is the another approach, right? You can adopt any of the approach. Okay, cool. So let me just show you. Okay, so here we got as a our training sentence where we have a 6,851 records and same number of labels. Labels are nothing but the target variable. So these are my sentences, and with respect to these many sentences, these many labels are there. And this is something we have a length for validation sentences. So to validate the model, we have a 762 records or 762 sentences. And with respect to each and every sentence, we have the target variable for 762 sentences. Right? So in that way, we have these two data sets. Now here comes the next step to apply the model. But do let me know, guys, can I directly apply my model over this text data? Can I do that? What do you think? Till this place, I have only text data, right? This one, this text information. Can I apply my model or any kind of a statistical technique over this text information? No, right? Yes. So ultimately, you need to apply the concept of vectorization. Okay. And since we are dealing with the deep learning based approach, so now it's time to see what are the things are available in the deep learning for a vectorization point of view. So let me just come to this point. Okay. Now, can you guys recall me what are the techniques available in machine learning as a vectorization technique? How we can transform or convert my text data into the numerical representation or vector form? Do you guys recall any one of those techniques? Yes, Mohit. Bag of word, binary weights, yeah. And if you guys recall TF-IDF, right? So when it comes to the machine learning, we have a techniques like binary weight, bag of word, and TF, IDF vectorization. And we saw like out of these three techniques, we saw the implementation of these two techniques, right? So bag of word is also known as a count vectorizer. And then we have a TF-IDF vectorizer. Apart from that, we have another technique which is called as a binary weights. It is also known as a one-hot encoding technique, OHE, one-hot encoding technique. Now, all of these techniques are statistical techniques, which comes under the machine learning part, right? Now, when it comes to the deep learning section, here also we have a couple of advanced approaches when it comes to the vectorization part. Okay, so we have something called as a word embedding. So guys, word embedding is something we have as a deep learning based approach to convert our text data into the numerical representation, right? Okay, we have another, segregation of this word embedding technique. So under this word embedding, we have two approaches, either continuous bag of words, CBOW, or skipgram. So skipgram is another technique. Sorry, skipgram. So these two are the specific case of this word embedding. And apart from that, guys, apart from that, whatever we have as a binary weight technique, which is a one-hot encoder technique in with respect to the machine learning part, same one-hot encoder technique we have in deep learning also. So like just like this binary weights, we have a something called as a what we call as a text vectorization. Text vectorization. So it is another approach available in deep learning, which will work just like this binary weight or one hot encoding, right? So let me just give you an overview idea regarding this text vectorization, or it is also called as the tokenization. This is not that tokenization what you have studied in pre-processing part, right? So let's call it as a text vectorization. So let me just show you, just explain you what are these, these two terms are, and some basic understanding of text vectorization and word embedding. Okay, so we have we are going to discuss the two approaches in the deep learning for vectorization. The first one is a tokenization or text vectorization. You can call it as text vectorization. And the second one is a word embedding. Right? Now let's suppose, guys, I have a an example sentence. Let's say I have example sentence like I like keras. Let's suppose I have this small sentence, I like keras. And I want to, transform this particular text sentence into its vectorization form using deep learning approach. Okay. So if I talk about the tokenization or text vectorization, right? So this is my input sentence. And if I pass this input sentence to text vectorization, so as I told you, it will work just like what we have as a binary weight, right? So let me just recall you the things related to the binary weight. So what binary weight will do? So binary weight will only, it will create a matrix where you have a values like 0 or 1, where 1 signifies that the token is present in the document, 0 signifies that that token is not present. The similar way we have in a deep learning that is called as a text vectorization. Now, what this text vectorization will do, it can adopt either of the methods. So it can, convert this particular sentence into vectors like, it can do like this. I is encoded as 0. Like, second word is a like, which can be encoded as 1. Third word is a keras, that can be encoded as 2. And if you have a more words, so that can be encoded as a 0, 1, 2, 3, 4, 5 in that way. So it will just provide some index or tokens to these keywords. And in that way, it will create a vector, right? So that can be the one approach which it can adopt. The second approach, what it can do, it can create a matrix like this. So it's actually an array. So what it can do, it will create a vector array just like this. So we have a first sentence as I. So it will do 1 where we have a first word as a I. So here we have a 1 for first word, and then we have a 2 more words like. So in the first array, we have these 2 values as a 0. Then in the second array, so second array will indicate this second sentence, which is a lie. So 0, 1, 0. Third sentence, third word, we have a keras. So the first 2 words will be 0 and the third word is 1. So in that way, it can create this kind of a vector array that can be represented, like that is used as a vector representation of this particular sentence. Now, the problem with this kind of approach is, here I have taken just a small sentence. But when it comes to the real time, guys, we have a very long sentences, right? So in that case, guys, what is the issue? This kind of a vector array, what is being created here, these are of very long length where there is only one value is present and the rest all of the values are 0. And this is with respect to each and every word, right? Let's suppose in a particular sentence, let's say I am just transforming a paragraph where we have a 500 words. So what it will do, it will, it will indicate the value 1 for the first word, and rest 499 for 499 words we have that many number of zeros, and this is with each and every array. So this is the drawback of this particular approach. So it will create very large matrix. It will create a very large vector array or this matrix, which you can't change its size. This is first thing. Second thing, so let me write here. What are the disadvantage of this particular approach? So first one is a very large matrix size. So matrix is nothing but this vector array. This is the first drawback. Second drawback is it will create a sparse matrix. Sparse matrix. Now, what is the sparse matrix? So guys, if you see this particular matrix, in this matrix, we have a number of, like tokens, either 0 or 1, where, okay, so if you see this matrix as in a, like as a whole, so you can find here, guys, there are very few values which are non-zero. I'm repeating it again. There are very few values which are non-zero. Most of the values are 0 only. So if you have a matrix like this where most of the elements are 0 and there are very few elements which are other than 0, that particular matrix is called as a sparse matrix, right? And if you are proceeding with this kind of a matrix for further analysis, so ultimately this is a matrix, and when you are applying any kind of a analysis, there will be some kind of a either matrix multiplication or some kind of a operations is going on over this kind of a matrix. So if there is a matrix multiplication, so where we have these 0 present, all of that information will get vanishes, right, in further steps. So that is a drawback with this kind of a sparse matrix. So generally we avoid this kind of a situation where we are getting, sparse matrix as the outcome of any kind of a matrix operation. So these are the drawbacks of this text vectorization. Is that clear, guys? What is this text vectorization and what are the drawbacks? Why we prefer word embedding? That is something I'm coming to this point. But yeah, is this point is clear, guys? Things related to that. There is one question. Keras means. Sumona, if you recall, the first class of the implementation of deep learning part, ANN. So there I discussed we have two libraries to implement that is very much useful in case of a deep learning hands-on. One is a TensorFlow, another one is a Keras. So Keras is a library which has a number of functions for a deep learning perspective. And this Keras is built on the top of TensorFlow, right? So we have discussed all those things. Sorry. Okay. Great. So guys, this explanation is clear to all of you, or any doubt, any queries, anyone? Cool. So this is something we have a text vectorization, and these are the drawbacks of the text vectorization approach. Now let's see how word embedding will convert these sentence into the vector representation form. So let me just clean this part. Okay, cool. So let's see how word embedding will transform this into the vector representation. So if you pass this particular sentence into the word embedding, so what it will do, guys, it will create a vector representation of this sentence like this. So for each and every word, guys, we have the vector representation for each and every word like this. So let's say for first word I, we have a vector representation like, let's say the first value is 0. Let's say 492, 0.581, 0.091, something like that. This is for first word. For second word, we have a vector representation like, let's say, I'm just taking some random values, 0.1002, 0.009, 0.716, like that. For third word, we have a vector representation like, let's say 0.281, 0.340, 0.801, something like that. So this kind of a vector representation is being created. This kind of a vector array is being created when you are applying the word embedding. Now, what is this vector representation? If you see, so here in this particular example, what word embedding has done, it has converted each and every word into three-dimensional vector. Three-dimensional vector representation, right? So 1, 2, and 3. Each and every word is being converted into three-dimensional vector representation. This is first thing. Okay. So the advantage of this kind of approach is you can tune the size of this particular vector array. That means you can decide what will be the output of vector dimension for each and every word, right? So in this particular example, we have a three-dimensional vector. You can also set it like a five-dimensional vector. Let's say 64-dimensional vector. That is something you can set, and that will be the fix. So in short, you can control the size of this vector array, right? And accordingly, whatever output size you will provide, that particular size of vector array will be created for each and every word. This is first thing. Second thing is, guys, here in the case of word embedding, you won't get this particular matrix as a sparse matrix. So whatever vector representation matrix you are getting in case of a word embedding, that will be the dense matrix. Dense matrix, right? So it will overcome the drawback of the text vectorization where you are getting the sparse matrix. So here in this case, you won't get the sparse matrix, you will get the output as a dense matrix. Now, third advantage of this word embedding is, which is very important. This particular approach, since it is based upon the neural network based approach, right? So word embedding at the backend utilizes something called as a neural networks. So whatever these values are you are seeing here, these numerical representation or this vector values, these values will get trained based upon data time to time, and it will get updated. So it will provide much better text to vector representation. So this kind of a representation will be much better, which can represent this particular sentence, right? Since it is a neural network based approach, so it can learn from the data. So this value will get updated as the model learns from the data. So you will get very much accurate representation of this particular sentence. So that is another advantage. So these are the advantage of this word embedding, which is a deep learning based approach. Right? Is that clear, guys? Let me check with YouTube, guys. Okay, there is one question. How are these values coming up in this matrix? So as I told you guys, this is a neural network based architecture. So at the backend, we have a couple of more complex calculation is going on. So let's not get into that part. So I mean, from the neural network only, how the neural network will start. So it will first assign some random values of the weight, and then it will start processing, right? So in that way, it will tune these values. So whatever values you are seeing in this matrix, it will get updated. Himanshu, these are not the updated weights, but these are the final output metric, which is a vector representation for the whatever sentence I have taken. I mean, it's not a backend calculation. It is I've just shown you the output, but at the backend, what is the calculation? So whatever we have discussed things with respect to the neural network part, the weight initialization, and the information is flowing from input to output layer, and then weights are being updated based upon the back propagation method. All of those things are there at the backend. So whatever is final output you are getting, I'm just taking that example. Okay, just a minute, guys. Okay, so let me reshare my screen. Cool. So I hope my screen is visible to you guys. So let me first show you how you can apply the text vectorization, and then I will show you how you can apply the word embedding. right? So guys, under the Keras layer, like Keras library, we have a module called layers. Under that, we have a method called text vectorization, right? So you can directly apply this particular method. So here we have initialized this method, text vectorization. And guys, there are a lot of arguments are there. So it's like max tokens. So max tokens are nothing but you can specify how many number of maximum tokens it can use for the analysis. So here you can specify that based upon your corpus, just take only let's say 1000 tokens. Based upon 1000 tokens, do the text vectorization. Or you can say that just take 5000 tokens or 10,000 tokens. So that option is there. You can select how many maximum number of tokens it can consider for the processing. And then guys, if you recall, in the text processing part, we have a two steps, like we need to convert all the text data into the lowercase, and we need to remove the punctuations. So here we have a one of the argument called standardized, and in the standardized we have an option called lower and strip punctuation, right? So just by using this particular option available, what it can do, it will automatically convert all the text information into the lowercase, and then it will remove the punctuations by its own, right? So that option is there. And then split the sentence based upon the space, then it will create a token, which is the word, and output mode will be the integer one. Those things are there. So here we are just initializing this text vectorization, and we are calling as a text vec. And once we have initialized this text vec, then you need to use a method called adopt. What adopt will do? So it will learn from these training sentences. That means whatever mechanism is there under this text vectorization, it will learn or it will apply those things over this train sentences, and based upon that, it will learn from this training data set. Now, at the system, the training process is completed. Now you can apply this particular method called text vec, which is a text vectorization over any kind of a sentence to convert into its numerical representation. Right. So here you can see here, guys. So I have just taken one sample sentence, like there is food flood in my city. And over this sentence, I'm going to apply the text vectorization. So it will, take the sample sentence as a list. So that's why I have used this square braces. So I hope you guys recall the list and, dictionary, list, tuples, all of those things. We have already covered that part, right? Cool. So it can consider the sentences in the form of list only. So under this list, we have passed this sample sentence. And here you can see, guys, this is the output, what it is being generated. Since it is just like a one-hot encoding, so what it is doing, it is providing a one token index for each and every word. So for there, the index value is, or it's not actually index, it's a token value is 74. That is the vector representation of this particular word called there. For is, it is 9. For flit, it is 232. For in, it is 4. For my, it is 13. For city, it is 182. Right? And you can check, guys, here. The shape is 1,6. That means we have a one sentence. And for this sentence, we have a 6 vector values. Right? You can also provide, some longer sentences. So, for example, just this sentence, there is a flood in my city and we are looking for help. So for each and every word, it is being converted into its vector representation. Since it is a text tokenization, so what this method is doing here, it will just, assigning some numerical tokens, or you can say vector tokens for each and every word. For there, 74 is represented as a 9. Flood is represented as 232, and so on. Right? So this is how you can use the text vectorization. But guys, apart from all the drawbacks, whatever we have discussed, there is another drawback in this case. So here, guys, we have not specified what is the sequence length of the output array. So you can see here, guys, if my sentence is small, the size of the output array is 1,6. If I have a larger sentence, the size is, for this particular case, the size is 1,12. So there is a non-uniformity in case of a output array, right? So ultimately, you need an output which is of same size. So that is another one issue. So this issue can be resolved with this particular approach. So what we are doing, guys, here, we are just trying to identify in our training sequence or training sentence what is the average number of token or words. That means what is the average length of my training sentence. So here it comes, the average length of my training sequence sentences is 15. That means on an average, in each and every training sentence, we have a 15 words. So we can modify this text vectorization approach like this. So here we are specifying, just take the maximum token as a 10,000, right? No need to convert each and every word. Just take the 10,000 tokens, right? And the whatever output sequence you are creating, so the maximum length will be 15. So these two things we are specifying here. Okay. So now if you convert any of the sentence into this text vectorization approach, so ultimately for each and every sentence you will get the output sequence length as a 15. For example, let's check with the same example. So we have a same sentence, sample sentence. I have applied the text vectorizer. So now you can see, guys, up to this point, we have a vector representation for each and every word. But since we have fixed that my output sequence length will be 15, so for rest of the words, so up to the 6, we have a vector representation, and after that, we have a value 0. So it will pad value 0 to make the output of a fixed size, which is of 15 sequence length, right? And if you pass any input, so in this case also, we have actually 12 words. So up to 12 words, we have the vector representation. And for 13, 14, and 15, we have a 0. So let's suppose you are passing a sentence which has a number of words greater than 15. Let's say this is a word number 12. Let's say after that we have a couple of more words. So this is a word number 12, word number 13, 14, 15, and so on. So what it will do, it will just take first 15 words to convert into tokenization form, this word like vector representation form, and rest of the words are being ignored or discarded. So in that way, it will fix the size of the output sequence, right? So this is something you can also apply, also mention some, hard code value. So here I have just taken one approach, that what is the average length of my input sequence. So you can just take like more than 15 or 20, 25 according to what kind of a data you are getting. And then we have discussed what are the drawbacks of this text vectorization. It creates a very huge matrix. It results in a sparse matrix, and it provides the static vector representation. So whatever vector is represented for there in this sentence, the same vector value you are getting for the next sentence. So it won't learn from this particular, like input sentences. So the drawback of this, text vectorization is being overcome by word embedding. So for word embedding also, we have a couple of arguments like input dimension, which is nothing but what will be your maximum vocabulary length. That is nothing but the maximum tokens. And the output dimension, so here we are fixing my output size will be of 128 vectors, right? So that means each and every word is being converted into 128 dimensional vector. So in that example, I have taken 3 dimensional vectors. But here I am fixing that it just take 128 dimensional vector. That means each and every word is being converted into 128 dimensional vector representation. Right? And then input length will be the max length, which is a 15 words. I have already specified, right? So this is something we have an embedding layer. And then just see one example. So we have just initialized this embedding layer as an embedding. And then we are going to apply this embedding layer into some sample sentences. So let's say we have this particular sample sentence, and we are going to apply the embedding layer over this particular sentence, right? So this is what you are getting in the output. Now here, guys, you can see here, we have this sentence. There is a flood in my city. And you can see, guys, each and every sentence is being converted into 128 dimensional vector representation. So if you see, first of all, the shape is 115 and 128, which signifies there will be one input sequence which is of length of 15, and each and every this sequence is being converted into 128 dimensional vector. So whatever this these vectors you are seeing, this like value 1, 2, 3, and up to the last, these are 128 vectors for each and every word, right? So let me just expand this particular array. So this is what we have, a first array where you have a 128 dimensional vectors. So this is how you can fix the output array size in word embedding, right? So we are going to use this particular approach only. So the rest of the things are same. I'm just using the word embedding layer to build a LSTM model over my training data set. And since this is a classification problem, so I'm using the activation function as a sigmoid for my output layer, right? For hidden layer, I'm using ReLU as an activation function. And the rest of the things are exactly same. The second phase is a compile the model. The loss is a binary cross entropy, metric accuracy, and I'm using the ADAM as an optimizer. And then like execute the model or fit the model over training data set. Here I'm using the 5 epochs, right? I can also pass, guys, there is another option available while you are fitting your model. You can pass the validation data. So what is the advantage of passing the validation data here? So the advantage is like this. So when the model start executing, so here you can see that what is the accuracy of the model over training data, what is the loss of model over training data, as well as what is the loss of model as well as the accuracy over this validation data, right? So this is the advantage, that in this particular execution part, you can see that how model is being trained and how well model is being performed over validation data. Both the things you can observe here, right? So you can see here, guys, over the validation data, I'm getting the accuracy as a 78% in the first epoch, 78% in the second epoch, 77%, 77%, 75%, like that. Okay. And then once your model is built, you can do the prediction over either validation sentences or text sentences, whatever you have, you can do that. And then we are just converting. So it will give you the probability. So these are the probability values, since it is a sigmoid activation function. And then these probabilities are being converted into the classes, either 0 or 1. All right. So this is the approach. So the thing is like, if you have a probability value greater than 0.5, so it will allot class 1, else class 0. So you can see here, the first probability value is less than 0.5. So that's why we are getting the here the class is being allotted as a class 0. That means it is not a disastrous. The second probability value is greater than 0.5. So it is being allotted as a class 1, which is that means this sentence is having the disastrous information. That means information related to the disaster and all. And this is over the validation sentence. So this is what we have, and the accuracy what we are getting over the validation data is 75.9%. right? So this is how, guys, you can use the deep learning based approach to analyze the text information. Is that clear, guys? Any doubt or any queries up to this part, anyone? Let me check with YouTube guys also. Yes, guys. Any questions, any doubt, anyone? Okay, cool. So let me just give 1 minute, guys. Just give me 1 minute so that I will be prepared with next part. Okay, guys. So let me share my screen. Cool. So up to this point, guys, we saw what is the LSTM architecture and how you can apply the model over sequential data, right? And then if you recall, guys, under the gated neural network architecture, we have another model which we call as the GRU, gated recurrent unit, right? So this is the modified version of the LSTM model. So this is what we have a LSTM internal architecture, and this is what we have as a gated recurrent unit GRU internal architecture. So it is another kind of a gated neural network model. And the key difference between the LSTM and GRU that lies in their internal structure and the way they handle the memory. That's it. So if you recall, guys, in the LSTM, we have a three gates: forget gate, input gate, and output gate, right? In case of a GRU, we have only two gates. Now, what are those two gates? Let's see. So here we have a something called a reset gate and update gate, right? We have only two gates. And if you see here, guys, so like what I have done, I have just taken a comparison between the LSTM and GRU, how they are different in terms of the different parameters. So over the gating mechanism, LSTM utilizes the three gates: input gate, forget gate, and output gate to handle the control, to control the flow of information. While GRU uses only two gates, one is a reset gate, and this is something we call as a reset gate, and update gate. This particular portion is called as a update gate. All right. So GRU has a more streamlined architecture compared to LSTM, since it utilizes only two gates. If I talk about in terms of the memory cell, so LSTM has a separate memory cell and hidden state. If you guys recall, we have a cell state and hidden state. In case of a GRU, it combines the memory cell and hidden state into a single state called HT. So this HT, it contains the information related to the memory cell as well as the hidden state. This is something you can see here. So you can see here, guys. Here we have only one output. Let me just show you this particular diagram. So in case of a LSTM, we have a two output. One is a cell state, another one is a hidden state. In case of a GRU, it combines these two output into a single output called as a HT. So this HT contains output from hidden state as well as the cell state, right? So this is something with respect to the memory cell. Now, if I talk about with respect to handling of memory, so LSTM has ability to learn when to read, when to write, and when to reset the memory cell content. So that makes the LSTM more capable of capturing and preserving the long-term dependencies. While in case of a GRU, since it uses a reset gate to decide which parts of past information to forget or update, and forget and update get determine how much new information is being incorporated. So GRUs are computationally less intensive than LSTM because it uses only two gates. So the number of computations or the whatever internal processing is going on, that is less in GRU compared to LSTM. Because in LSTM we have a three gates, so it has a three different kind of a processing, right? So this is something we have a LSTM and GRU architecture. So both are the gated architecture, right? But as I told you, most of the times we go with the LSTM model. Like I've rarely seen an application where it is utilizing the gated recurrent architecture, right? Okay, so up to this point, guys, we have understood the basics of the neural network and how the different neural network architectures are aligned, like ANN, CNN, RNN, and what are the modified form of the RNN, which are the gated, neural network architectures. Now let's come to the specific application of the generative AI. So one of the models generative AI uses, that is something we call as the sequence to sequence models. Now, these sequence to sequence models at the backend, they consist of two RNN models. And let me just ratify it. Especially it's a two LSTM models, right? So if you see the architecture of sequence to sequence models, they have at the backend two LSTM models. And the first LSTM model is called as a encoder. Second LSTM model is called as a decoder. So we have something called as a encoder decoder architecture. Now, these kind of models, sequence to sequence models, are most commonly utilized in applications like machine translation, text summarization, speech recognition, question answering system, developing the chatbots, those kind of applications, right? So let's see, some more detail regarding this sequence to sequence model. And let's try to understand its architecture and what are other things are there. Okay. So before proceeding, guys, any doubts or any queries, anyone? What about YouTube, guys? Okay, great. So let me share my screen. Okay, guys. So let's see the sequence to sequence model architecture, where we have two things. One is an encoder and one is a decoder. So this is something, guys, how sequence to sequence model looks like. As I told you, sequence to sequence model is based upon uh, two LSTM architecture. Can be LSTM model or it can be RNN. But when it comes to the real time application, we use the LSTM architecture only. So it is using two LSTM or two RNN architecture. One is called as an encoder, another one is called as a decoder, right? Now, with whatever input data, which is a sequential data, whatever sequential input data we have, we provide the input to this encoder. Encoder will do, certain kind of a processing, and it will generate the output, what we are calling as a context vector, right? So whatever encoder is generating the output, we called as a context vector. That will be the input to the decoder. And there is some, a black box kind of a thing. That means there is some processing is going on. And then decoder will provide the output. So this is, you can say, a top view how this sequence to sequence model looks like. We have an encoder. This box is an encoder. Don't worry, guys. I will come to all of like each and every point. What is this box of encoder? What is this decoder and all? So we have something called as an encoder. So we provide input, which is a sequential data, to this encoder. Encoder do some kind of a processing. It will generate context vector, which is the input to this decoder. Now decoder will take context vector and it will try to decode the information, and whatever processing is being performed based upon that, it will generate the output. This is something we are calling as a sequence to sequence model. Okay. So this is what we have. We provide input like X0, X1, X2. So this is a sequential data to the encoder network. Encoder network will generate the context vector, which is the hidden state output. And whatever output is being generated, that is input to the decoder network. And then decoder network will, for each and every time instance, decoder network will generate the output. So at time instance t, at time instance t plus 1, time instance t plus 2, and so on. Right? So we have an input at time instance, let's say t plus 1, t plus 2, and let's say here we have a t dash plus 1, t dash plus, something like that. So this is the a top view how sequence to sequence model looks like. Now let's get into this encoder network and decoder network. So guys, before that, let me just explain you the things related to encoder and decoder. So encoder process each token in the text input sequence. It creates a vector of fixed length, what we are calling as a context vector. After going through all the tokens, encoder passes this vector onto the decoder. This context vector is built in such a way that it is expected to encapsulate the whole meaning of the input sequence, and that helps the decoder to make accurate prediction. Right? So decoder will generate the text based upon this context vector only. And it is being expected that the context vector will contain all the information related to the input sequence. Okay. So this is a one step deeper architecture of the sequence to sequence model. So as I told you, sequence to sequence model is having the two LSTM architecture. The first one is called as a encoder. So whatever this green box you are seeing, that is the encoder. Whatever this second box you are seeing, that is the decoder. Right? So in the encoder is nothing but, guys, it is a LSTM neural network architecture only. So we have a different LSTM, layers. We have a different neural networks based upon LSTM model architecture. And then since we have a sequential data, so let's suppose we have a sequential data like this. Nice to meet you. And based upon this input data, decoder will generate the output. So what we'll do? We provide this sequential text data at each and every time instance to these models. So like at time instance t, we provide nice. At time instance t plus 1, we provide 2. At time instance t plus 2, we provide meet. At time instance t plus 3, we provide u. So like sequentially, these words will be input to this LSTM architecture. And just now we saw, guys, before this, this conceptual part, we saw hands-on how LSTM model handles the text data, right? Sequential data, which is the text data. So we provide this all of these words input to this LSTM architecture. LSTM will do the processing, internal processing. So all of these, LSTM blocks are nothing but the neural networks, where we have the number of hidden layers, right? So it will perform the internal processing, which is a simple neural network processing. And based upon that, each and every layer will generate the output. You can see this is the output for each and every LSTM model, right? And then whatever is okay. So there is one important thing with respect to this encoder, guys. Whatever these outputs are being generated from the encoder. So this is with respect to the encoder. In case of a sequence to sequence model, we discard all of these outputs, right? We will discard all of these individual outputs which is being generated by these LSTM models. And whatever output is being generated based upon the cell state and hidden state. So I'm sure now you guys understand what is the cell state and hidden state with respect to the LSTM, right? So if you recall the LSTM architecture, so we have a 2 output. We have a 3 input in LSTM model and 2 output. One is a cell state CT, another one is a hidden state HT. So this is something what we are getting 2 outputs, since here the outputs are showing in a single arrow, but there is a 2 outputs, HT and CT. So these outputs will be the input to the decoder. And whatever output is being generated by these these individual LSTM models, all of these outputs are discarded in case of a sequence to sequence model, right? So the output from the hidden state and cell state is the input to the decoder module. Is that clear, guys? The things related to the encoder module. Any doubt with this part? Anyone? Guys, this encoder part is clear. Okay. Yeah, great. Let me check with YouTube guys also there. Great. So let me share my screen. Okay, cool, guys. So this is the top view how encoder will generate the output and how it will do the processing. Now, whatever output is being generated from this encoder, I mean the hidden state and cell state output, that is the input to the decoder. Now let's understand, guys. There is a very interesting part in decoder. Decoder also contains the LSTM neural network architecture, right? Since that's why we are calling sequence to sequence model as a 2 LSTM architecture or 2 RNN architecture. So that means the first LSTM model is for the encoder part and the second LSTM is for the decoder part. So decoder is also contains certain number of LSTM layers. And then how the decoder will generate the output. So see, guys, in the encoder actually there is a one more block. Okay, I will come to this part. Okay, so this is the input for this decoder module. decoder, and whatever is the first LSTM block of this decoder, it will take this input, and we also provide something called as a start of the sentence. So actually, in this encoder module, we have a last block, which will indicate, here we will indicate this is the end of sentence. So you need to, define where this particular sentence ends, and decoder will in the decoder, you need to specify where a particular sentence starts, right? That means the start is an indication that decoder will start generating the output. End of sentence will indicate that encoder will understand this is the end of particular sentence, right? So in that way, we have these two, tokens: end of sentence and start of sentence. Anyways, so this is the input for the first layer of its first LSTM module in case of a decoder, and based upon this particular information from the encoder, decoder will generate the output word, a particular word, right? Now this word will be input for second LSTM module. You can see here it is generating Ravi, which is the input for the second LSTM module. And since it is a LSTM model, so whatever hidden state output and cell state output is being generated by this first LSTM block is the input to the second LSTM block. In short, for second LSTM block, there will be two inputs. Actually, there are three inputs. One is the hidden state input for this first block, cell state input from this first block, and whatever output this first LSTM block is being generated, that is also the input to this second LSTM block. And the same process repeats for rest of the LSTM blocks. So whatever output is being generated by this second LSTM block, this one, that is the input for third LSTM block. And what are the other inputs? Whatever hidden state and cell state is being generated by second LSTM block. And in that way, it will generate the output sequence. And whenever, at the end, the decoder will generate something called as an end of sentence. Right? So this is the very basic understanding how sequence to sequence model performs. Right? Is this architecture is clear, guys? Okay, cool. So I have a question, guys. Here you can see in the encoder part, we are providing these words as input to the encoder. What do you think? We provide these words directly to these encoders, or there will be some kind of techniques we apply? So actually, you need to apply vectorization part, right? So that part will be there. So you can see here. Yes. So you can see here, guys. This is the little bit more detailed, visualization of this sequence to sequence model. Whatever input sequence we have, first of all, you need to apply this input sequence to embedding layer. This embedding layer will convert these input data, text input data, into the vectorization form. This vector representation is being fed to this LSTM model in the encoder side. So this is something I'm discussing with respect to the encoder side, right? And whatever output LSTM cells are generating, we discard these outputs in case of an encoder part. In case of an encoder, we discard all of these outputs, right? And obviously, there is some end of sentence token is there. We only, taking forward this cell state and hidden state output from the last LSTM block. This is something we are calling as a context vector. Context vector. right? So whatever output is being generated by this hidden state and cell state, we called as a context vector. And this is a vector representation, guys. It's not a single number. It's a vector representation. Okay. So you need to provide the, some kind of a vectorization technique over this input text data. And then when this context vector is being input to the decoder module, so from the decoder module, the first LSTM module will take the output of this context vector, which is generated from the encoder layer as an input, and we provide the start of sentence. Also, you need to pass this from the embedding layer. Whatever output is being generated by this LSTM model based upon the activation function, this particular output word is the input to the second LSTM module, and this word is being again converted by this embedding layer into the vectorization form, and this LSTM model will take input from the previous LSTM cells hidden state and cell state output, and this current word vector representation form, it will generate the output, and the same process repeats for each and every cell till the last. So the last cell will generate end of sentence, so that the model can understand this is the final output. So in this particular example, if this is your input sentence, this is what the sequence to sequence model is generating as the output sentence, right? So this is something okay. So there is one question. Decoder work is to decode, encoder is to decode. Yes. And encoder is to encode how a sentence. Okay. Encoder is to encode how a sentence is break into half, and then some context to provide. Okay. So guys, don't visualize this particular thing like we just encode this nice to some particular encoded representation, this to some particular encoded representation, and the decoder will it will just decode this particular numerical representation as a nice. Don't visualize this particular thing like that. Here we have a name like encoder and decoder. That doesn't mean that you have a particular word, let's say nice, and encoder will encode it like, let's say, a particular value like, let's say 10, and decoder will convert this 10 into nice. This is not the process here. Guys, we are discussing the generative AI model, which is a sequence to sequence model. And what is generative AI? It will generate the text, right? How it will generate? Whatever LSTM models we have. So what this LSTM models will do, it will generate something called as a cell state and the hidden state, which is the context vector. And this is not a single number. It's a huge vector array, right? And what the information this context vector contains? It contains the information like how these words are, like how important these words, and in terms of the context, how these words are, interlinked. So based upon that context value, this decoder will try to generate the possible outcomes. For example, if we have a sentence like nice to meet you, let's say we have a couple of more words like meet you, let's say yesterday afternoon. So what this encoded, what the information this context vector will contain? So it will contain the, how the words are interlinked in terms of the context. So we have a afternoon, we have a meet, we have a nice. So decoder will try to, generate the text like like this person met with some other person afternoon. So probably it was a lunchtime, right? And it was nice to meet. So like there are a couple of, things are interlinked. And all of those processing is being performed by LSTM model. Okay. This attendance link is there in the chat box. Please mark your attendance. So this is a detailed explanation regarding the encoder block and decoder block. Let me show you. Encoder part is the LSTM cell. It is fed in the input sequence over time, right? It tries to encapsulate all its information and store it is in final internal state, hidden state, and cell state. That means whatever we have a final LSTM block. So this from this final LSTM block, we are getting two output. One is a cell state output and hidden state, right? The internal states are then passed on to decoder part, and this particular output we are calling as a context vector. So this is something we pass to the decoder part. In the decoder, it will try, it will use to try to produce the target sequence based on this context vector. And as I told you, this context vector contains the information regarding how important a particular word is, how, like what is the in which context that particular word is being used, how that particular word is linked to other words, right? So this is something we are called as a context vector. And as I told you, output at each time instant of the encoder part are discarded. So each and every output of individual LSTM model is being discarded. So we will only carry forward the hidden state and cell state output of the last LSTM cell in the encoder block. Okay, so this is what we have. So for each and every time instance, like at the time instance t, we have a nice t plus 1, we have a next sentence, next word, t plus 2, and so on. And whatever output is being generated by these LSTM cells, all of these outputs are discarded. We will only carry forward the context vector, which is nothing but the final state of the encoder, which is nothing but this hidden state output and cell state output from the last LSTM cell. So it is being assumed that this context vector will try to capture all the relevant information from the past LSTM cells. It is being assumed, right? But in real case, when it comes to the practical scenario, so we have a number of LSTM cells, and whatever this context vector is being generated, since we are discarding these outputs, right? So whatever this context vector is being generated, that context vector probably captures most of the information which is based upon some recent LSTM cells, not from the past LSTM cells. So like this particular point, I will explain probably in next session, because from this point, we have a couple of other architectures. So for the timing, let's understand in this way. So we have a context vector, which is assumed that it will contain all the relevant information from the past LSTM cells, right? And this information is being passed to the decoder part. So after reading the whole input sequence, encoder passes internal state, which is nothing but the context vector, to the decoder. And here we get the prediction as the output sequence. So just like that. And in the decoder part, as I told you, whatever output is being generated by each and every LSTM cell, that is the input to the next LSTM cell, right? And apart from that, since it is a LSTM cell, so whatever is the hidden state and the cell state is being generated by each and every LSTM cell, that is the input to the next LSTM cell also, right? So this is the detailed, graphical representation of the sequence to sequence model. Attendance link is there, guys, in the chat box. Okay, is that clear, guys, this part? Any doubt or any confusion to understand the basic architecture of the sequence to sequence model? Anyone? Okay, there is one question. What are the inputs in decoder part? So let me share my screen to show you. Okay, I hope my screen is visible. Let me just show you from this point. Okay. So guys, the question is, what is the input to the decoder part? So this is what we have as a decoder block. And if you see in the decoder, we have a only one input, which is the context vector that is being generated from this encoder block. So this context vector is the input to the decoder block, context vector. And as I told you, it is assumed that all the relevant information which is present in this particular sequential text data is being captured by this context vector that is being assumed, so that we provide this context vector to the decoder, and then decoder will start executing this context vector, and based upon whatever relations or things are present in this context vector, it will try to generate the output sequence. Clear, guys? Attendance link is there, guys. Please check the chat box. Is that clear, guys? What is the input to the decoder part? Okay, great. Why this picture is confusing? I'm not sure why you guys are getting confused. It's very simple. This is what we are getting from the encoder. That is the input to the decoder. And this is something we are calling as a context vector. Right? You guys recall this LSTM output? Let me just show you. This LSTM cell, this one. So each and every LSTM cell will generate two output, right? Cell state and hidden state. So whatever is the last LSTM cells, cell state and hidden state, that is the input to the decoder. And inside the decoder, we again have a different LSTM cells. Yes, Sumona. You can provide any kind of a sequential data in this network. Start Ravi looks like as an. Oh, okay. So you are confused with that sentence. Let me come to that part. So Ayushman, if you see here, okay, if you see here, this is not the decoder. This individual cell is not the decoder. This complete block is a decoder. This is first thing. So if you ask me what is the input to this decoder, input for this particular block is the context vector from encoder. This is first thing. So don't get confused with this kind of a input to this LSTM cells. A particular LSTM cell is not a decoder. This complete box is a decoder. Inside this decoder box, we have a different LSTM cells. And these cells are just now what I have showed you, a particular LSTM cell, right? Where we have a two outputs and three inputs. Okay. So you can check here, each and every LSTM cell is having two output and three input. So if I just check with this particular LSTM cell, what are the three inputs for this LSTM cell? One is this HT, CT, and this start token. Right? So this is the token which we provide that this is the starting of decoder part. Okay. And what are the two outputs of this LSTM cell? One is the HT and C, let's say HT plus 1 and CT plus 1. And along with that, it will generate the output. For second LSTM cell in the decoder, what is the three input? So one is the HT plus 1, second is the CT plus 1, and third one is the whatever output is being generated by the first LSTM cell, this Ravi. This Ravi is the input to this second LSTM cell. So in that way, we have a input to this encoder, as well as inside the encoder decoder, we have a LSTM cells. Is that clear now? Great. Great. Let me also check with YouTube guys. Meanwhile, any other questions, guys? Anyone? Don't worry, Arpit. All of these materials and hands-on exercise will be it will get available over the LMS portal. Don't worry about it. What is softmax? Okay, so softmax. Okay, let me just show you once again. Okay, so guys, softmax is nothing but when like here it is being like visualized as separate part. So actually, whatever neural network you're using some kind of a activation function, right? Based upon the activation function, the node will generate the output. So it is being assumed that, let's say, we are using the softmax as a activation function, right? So based upon that, we are getting this output. But yeah, it totally depends upon which kind of a problem statement you are dealing with. So this is what we have, guys, as an introduction to sequence model. And probably in the next session, I will discuss a couple of more details regarding this, modification over the sequence to sequence model. And then we'll see a couple of what you can say practical, use cases of the generative AI. So with that, guys, any other doubt, guys? Anyone? Himanshu, whatever hands-on I have discussed, in that I have done step by step only, right? So when you go through this, Zipter notebook, you can see that each and every cell I have specified what I'm doing and what are the different parameters I have assumed. So all of those things are step by step only. Okay. Any other doubt, guys? Anyone? What summary you are asking, Himanshu? Like summary related to which part? Okay, I will try to do that. But like, I'm not sure if I get the time, I will do that. Okay. Yeah. Okay, guys. So if you don't have any other questions for me, so over to Amar. If you have any question related to the LMS portal or study material, uh, Amar can help you.
Yeah, sure. Thank you. So participant, I shared the attendance link. So please mark your attendance. So Mona, we already rolled out that certificate. If your attendance is more than 60%, check your email. There is one participant, Arpit from the YouTube. So at the Excel, please provide notes and required dataset. So all the notes are available on the LMS. You can visit once. Okay, I think there is no more questions. So thank you so much for joining the session, and we'll meet you on Monday. So bye bye. Good night.